Okay, so there's one thing that I skipped in class this week, and I just want to prove it. So just for completeness. So in class, so maybe just to recap. So in the proof of expanded mixing lemma, there was a main step, which is we claim that we say that sigma 2 is exactly this quantity. And once we can prove this, we are done. But, and then, oh no, sorry. And then to prove this equality, we start with this equality, where in class I actually just write that this is the same thing as sigma 2 is the same thing as maximizing over everything, and x h and then I said that this is the same thing as this, but I didn't I kind of hand wave why they are the same, so now I'm gonna prove this thing directly. Yeah. Okay. So do you feel like you need more context on what is this equality before we go to prove it? Okay, it's good, right? Or, okay. So basically, to prove this thing, we will, I just need to recall you about, let's, instead of looking at this matrix, let's take any matrix M, and we look at the singular value decomposition of M, where you basically can, for any matrix M, you can decompose it into this, where this is like a diagonal matrix. And each of these consists of unit vector on each row or column. That is, you can just write this thing as this sum, where each u, I, and v, I are unit vectors. And the thing here is called singular value. Okay? So this is just singular value decomposition. So if you are not familiar with it, there is this book by Avrim Blum and others, which give a really nice introduction to this decomposition and the proof also, and also mention a lot of its application in data science. So it's quite nice. What we will need from this decomposition is just that for each I, basically Vi will be mapped to Ui. So it's kind of similar to eigenvalue, but now you apply Vi, you get Ui with this scaling. Yeah. And also for the largest singular value is basically the norm of the matrix, which is you ask like what is a stretch that M maps X to. Like if X is of size 1, is a unit vector, you ask like what is the maximum stretch that M can map X to. Yeah. Okay, so that's the two things. And now we just need this equality. So basically we will say that the sigma 1, the largest singular value of M, can be written as maximizing over Z and W, where you try to multiply Z and W from both sides and divide it by the norm of both. This is not hard to see actually. The reason is that if you take any, so let's prove this first. So if you take any Z and W and like multiply Z to M to W here, then just by Cauchy-Schwarz, right? You have that you just apply this. You have Cauchy-Schwarz where one term is Z, one term is MW, you get this. And by definition of the norm, this is at most MW, the norm of MW is at most the norm of M times the norm of W. And then the norm of M is just the first singular value. So by rearranging, one sec. Okay, sorry. We are proving this direction. Yeah, by rearranging, we get this. Yeah. So that's one direction. Now we just need to show that there actually exists Z and W so that this inequality holds with equality. And if you just take Z to be U1 and W to be V1, then we can see that when you multiply this together, then this thing is just this by definition of like from the property of singular value decomposition, and this is just you achieve this. Okay. So they are really equal. You get equality here. And also, singular value of the first singular value of M is nothing, but if you look at, suppose that now, okay, if M is symmetric, and so like so there exists like an eigenvalue, real eigenvalue of M. You have, there are real eigenvalue which, and you write it down as this. Just sort the eigenvalue of M. Then the first singular value of M is nothing but you take the absolute value of this and you take the maximum one. Yeah. And yeah, the proof is quite simple too. Well, because if you look at the singular value square, then this is like a norm of M square, which is this. And then you expand the definition here. Norm square is nothing but x times x. And norm of this square is just this thing times this thing. But now we see that this is exactly, this is just m square because m is symmetric. So this is now just the first eigenvalue of m square. But yeah, the first eigenvalue of m square, like the eigenvalue of m square is just like for every eigenvalue of m square actually is like, so eigenvalue of m square can be written as square of eigenvalue. And if you take the largest one, then you will get, it will be like the largest eigenvalue of m square, it can be either like the first one or the last one from eigenvalue of m, and you square it. So, and then because you have this, so basically this thing is this thing, equal. So you, if you remove the square, you get the claim. Okay. Just take the square root. Yeah. So now, yeah, we are done, because come back to our context where we look at the normalized adjacency matrix, and you remove the first, like minus it with this, where V1 is the first eigenvalue, first eigenvector of A prime G. You take M to be this matrix, right?
Is it the normalized reflection?
This is this is normalized adjacency matrix. So this is from the expander mixing lemma, right? So in that lemma, we kind of work with A prime, not N. Yeah. Yeah. So yeah, we work with A prime, and this thing is just the first eigenvector of A prime. Yeah. Okay. So now, yeah. So we want to prove that, yeah, this is what we want to prove, that sigma 2 is this. And how to prove that? We take M to be this. This is M. And we can see that the first singular value of M is just the maximum of absolute value of the first eigenvalue and the last eigenvalue. But this is nothing but the second eigenvalue of A prime, right? Because you look at the first eigenvalue of this thing but you remove the first one, the first eigenvalue of A prime. So it becomes the second eigenvalue of A prime here. For the last one, it stays the same. But now you just need to recall that this is just how we define sigma 2 in class, right? Sigma 2 is really just, we define sigma 2 to be the maximum over all I, which is not 1, the lambda I of absolute value of lambda of A prime. But which is the same thing as this. Is it clear? Okay, right. So now, yeah, we have that sigma 1 of m is sigma 2. Is our sigma 2. So I just write sigma 2 here is sigma 1 of m. But we saw just like from the variation characterization of sigma 1, this is just the same thing as we try to maximize over z and w from both sides, where the thing in the middle is m. This is m. And that proof the equality that we need. Okay. Okay, so that is the thing that I missed in class, and now let's go to some exercise. I think there is some, right? Yeah, this one. Show a deterministic algorithm that you can solve vertex connectivity just by using this minimax flow. Okay. So I will just give you some time to think. Like maybe think of what if k is 2, kappa is 2. How can you do it in just 2n max flow times or 3n or something?
So we can find whether a vertex belongs to max flow on the separator or not using finding kappa of x, right? So we will find kappa of x.
Actually, I think you just pick kappa plus 1 vertex to the single source max flow. Each of them take O and max flow. And then just take the median mass.
Yeah. That's right. So let me just repeat. Yeah, so suppose that, so let's say that kappa is the size of vertex min cut, right? So let's write this. This is L star. This is just some min cut. And let's say kappa is 2. So there are just 2 vertices here. And we know that as long as if we can choose any node outside H star, let's say X, and if we compute kappa K, kappa X, then we are done. But yeah, we don't know where is a good X, but we know that there are very bad guys, there are very few bad guys that we can choose from. So as long as we choose kappa plus 1 nodes, we know that one of them must be outside S star. And just compute the kappa x for each of this set of size kappa plus 1. One of them will be good for you.
But we should guess the kappa.
If it is just randomized, then, oh, no. We don't need to guess kappa.
Just do one by one and then check down the number of rounds.
So, okay, I see. So, let's see. Do we need to guess kappa? I mean, here is like,
But how do we know?
one sec. Right. So so one thing that works for sure is that if you are given some parameter k and you want to know if min cut is kappa is less than k or not, you can choose k plus 1 nodes.
So we need upper bound.
Right. So if you have an upper bound, then we should be fine for sure. But if we don't have an upper bound,
We can just keep choosing previous one or round by round. And once we get the answer, the minimum cut size of the current of the order cuts is less than our number of rounds, then we finish the algorithm.
really, does it just work?
Then we can finish it in half hour.
Let's see. One sec.
I can guarantee that at the kappa plus 1 round, the answer is less than kappa.
Yeah.
It's not more than kappa.
Right. I see.
So the time complexity is at most 10 times kappa maximum cost.
I see. So I see.
We can start from 1 to keep on going.
But we add up with n squared.
If kappa is actually n, then of course we will take n square.
Right.
But if kappa is not n, we will stop way ahead.
Very good. Yeah.
But how do we know the kappa y is the minimum? Maybe there is like
So we really do this, like we repeat for I iteration. If there is, like we repeat for I plus 1 iteration. And if there exists any candidate such that kappa x is less than I, then we are done.
but what if we keep choosing vertices from S? Like
Then
the
if we,
cut between vertices in S cannot guarantee like there are some values.
so if we keep choosing the node in S, then
Yeah, we can
then it will be not be like,
keep getting minimum values at each step. Can be less and less. So how do we know like which hand?
so
Like
let's see. So
between vertices in S can we choose can be less and less.
let's, yeah, that, one sec.
Is there any problem by just looking at the kappa plus 1 round? Second round we must have the answer more than kappa. Then we can add here.
Let me think. So is it like, is this true that if
So what if kappa minus some value is the minimum of the all previous minimum cuts? Should we stop or not? We don't know.
say it again, sorry?
Like if we we get like kappa minus some number. At step kappa minus some number, we get a minimum value of all the previous cuts. Should we stop or not?
No, we won't stop at kappa minus x. We'll be.
How do you know this is kappa minus x? Like it's the minimum value of all previous cuts.
Is that the minimum value?
How do you decide you should stop or not?
Like right now, the claim that that I think might be true is this. I'm not sure yet. Is that suppose so the algorithm is really just keep computing kappa x. That's the algorithm, right? And if at round I, the min. So, and let's say x1 up to xi is just the choice of vertices we have chosen so far. And if this thing, j at most I, if less than I, then we claim that kappa is this thing. So that's the claim. Like, or in the other word, this is less than at most I plus 1, I minus 1. Is this true? Because yeah, it seems true, but why is it true again, actually?
You can consider in two cases. The first case, I less than kappa.
Mm-hmm.
And I less than kappa, if we get anything less, no more than I minus 1, that is it. The first case is I no more than kappa. And there is nothing, no vertex cut with size less than I minus 1.
So if I is actually more than kappa, then we are done. If I is
Smaller than kappa, so
if I is smaller than kappa,
that's not okay.
then
How do you know I is less than kappa?
If I is less than kappa, then the property will not hold.
It can, because we have vertices in S, and the cut between vertices in S can be anything, right? They can also be minimum cut pattern or not.
but
Wait, that won't be valid, right? Minimum of kappa of xj, j less than equal to I won't be less than equal to I minus 1. It will be kappa minus x minus 1, which is not possible. So let's say I is equal to kappa minus x.
It can be a minimum cut,
Yeah.
like the minimum cut of S.
yeah, I think let's see this. Suppose that I is less than kappa, but this thing is strictly more than kappa, right? Suppose for contradiction. Yeah. Then what do we?
So we can prove it
Then we would have that. Then we would have that. This is at least I. But this contradicts this thing. So it cannot happen.
It's larger than 1.
Because
Because every vertex cut is besides that one, Palace how about is the minimum size of the police?
For example, in the doubt you have, you're telling that it's kind of image at kappa minus x, right? So you have kappa and you have a minimum value at kappa minus x. That's the question, right? How do we know we'll stop at kappa minus x? Whether to stop or not at kappa minus x. That's the question, right?
I think this is just, but anyway, this is just a proof, right? If I is more than kappa, we agree this is fine. And if I is less than kappa, but somehow, like, we don't have, like, our answer is not really true. That is, this is more than kappa, then we know that this thing is also more than I. But yeah, this would contradict our like termination condition. So okay. Okay, good. Is it at least is this proof okay? Yeah. Okay, is there other exercise? It seems to be not the case. Yeah, by the way, I really think that this problem is very interesting. Like, can you actually compute kappa in less than n max flow? Kappa x in less than n max flow? Yeah, there is kind of other open problem that I know, which if you can improve, then you will improve some state of the art of other problem too, which is the same problem. So here is like about deterministic algorithm. If you want randomize, even that it's not on top of my head how to do it actually, but if you get something randomized here, it wouldn't improve this algorithm because we need it to be deterministic. But actually getting this less than n max flow randomized here is quite interesting too. But there are other problem which is very similar in flavor, which is now you have a directed graph. You have root x. There are direction. And let's say that given any cut, you define the cut size to be just one direction. So maybe let's say that for even given a cut S contain X, then you consider the size that go out, then the total weight actually is like G is directed and weighted. So you consider like the cut that contains X and you look at the total weight going out of the cut. Okay. And the goal is to find such minimum cut. So basically so you want to find this cut S that contains X, but not everything. It should contain something else too. Like there should exist something outside the cut, okay. such that this thing is minimized. Right. So this is about edge cut. It's not about vertex cut. Like we count the total weight going out of a cut here. Just very like, it turns out that if you want to compute this, then clearly n max flow is enough. Just by take X and compute max flow for like directed max flow from X to everyone else. Right? N max flow is enough. Known N max flow. But quite recently, my co-author and I show that something like square root n is enough. So this is quite interesting, but yeah, anything below square root n would be interesting. But actually, let me point out our bottleneck, the place where we got stuck. So maybe, actually, to write this thing, this is just the same thing as, let's say that lambda x y is just mean xy cut. And so this is just like mean over y, not x, lambda xy, right? So the bottleneck that we got stuck at is this thing, which is, so instead of you have x here, now let's say that you have some terminal set t, and what you want to compute is minimum of y in t, this thing. So here is just like the set t is basically everything outside x, every node outside x, but now think of t is of size maybe square root n, yeah. And we want to compute this thing, like the minimum mean cut from x to all of this. But we just want one number, not just t not all of them. We just want the minimum one among this. And yeah, and basically, so T max flow is enough, but anything which is not trivial is not known for this. Like when T is small enough, yeah, when T is like log root n, we don't know how to get anything better than just T max flow. So this is like a open
How did you find that set T?
T is given to you.
No, in your case, rooted.
It's complicated. Yeah. So, yeah, like it's a bunch of things combined. Yeah. Right. Okay. So, otherwise, I think maybe we can just. Is there anything you want to talk about? Otherwise, I can talk about the open problem that I have listed and some of the problem I didn't talk about yet. Should we do that? Okay.
So yesterday Shannon told an idea, right, where we find for improving the gap, we have to put the edges for fixing the vertices. So in that case, initially you were doing log n iterations to actually find the whole fix of everything. So now if you just find another non-edge and put the edge.
So yeah, we shave log from
shave log.
yeah, it would shave a log but using Chang'an suggestion. Yeah, right. Right. Yeah, but the advantage of the approach that I presented in class is only that we really reduce the problem to computing kappa of x. And kappa of x we might be able to improve to solve that faster than n max flow.
Okay. So because we are taking W and finding kappa, so that can actually lead us quicker to the kappa.
Yeah. Right now we don't know how to get better than n max flow to solve kappa of W. But if we can, then it would immediately improve the whole algorithm. Yeah. Yeah, this is very interesting. If one can improve it, this is going to be very nice. Yeah. Yeah.
In the previous slide which you presented, the order of log n log and max flows, is it already there?
Yeah.
There, little above.
Above.
Right.
On the right.
Yeah, the n log n max flows is written. So is that algorithm already exists?
N log n. Well, here just ON is enough, right?
Yeah.
Yeah.
No, but so you wrote n log n max flows on the top.
Oh.
That algorithm already exists.
So even n is enough. Even n exists. You can just compute it one by one.
Okay.
By n log n here, I mean that it leads to n log n max flow in the whole algorithm here.
Oh.
Yeah. Yeah. Okay. Oh yeah, this is just the problem that I just mentioned to you just a moment ago. So it's called Steiner rooted directed connectivity. So it's just this problem, yeah, where you have x and you have t, and you want to compute, minimum. Yeah, it's this problem. So Okay. Yeah, and this one I also mentioned in class. Yeah, and okay. This one is maybe one of my favorite problem. So basically, like here we say that we can compute, like given x and y, you can compute kappa xy in one MaxFlow call, right? So right now, I kind of say in class that MaxFlow is kind of quite fast, but it's not near linear yet. It's like still like polynomially slower than linear. Now you can ask, okay, just to compute this thing, like it's just the maximum number of vertex disjoint path from x to y. If we want this number, but only approximately, can we do it faster? Like, can we do it really in linear time? So just this year, my co-author and I show that you can compute this approximately in time, which is something like m plus little 1. And the dependency on epsilon is very bad. It's something like, I'm not sure. Something like this maybe, I don't know. So now the question is that, can you improve it? Can you really get it in close to linear time? Like very like m times polylog, and the dependency on epsilon should be polynomial.
Are xy given or?
Xy is given. Yeah. So it's really like a vertex MaxFlow problem here. You have x and y, you want maximum number of vertex disjoint path, approximately. Yeah. So the reason to hope for this is that, yes, so this is with, by the way, Bernstein, Gutenberg, and me this year. So the reason to hope for this is that if it is just about edge MaxFlow, so the graph, like you want a maximum number of edge disjoint path, not vertex, then you can do it in this time. So if it is for edge MaxFlow, then you can do it in this time. And algorithm is nice and quite simple, actually. And by the end of this class, you will see actually how to do it. But I might only present how to do it in this time. This is the thing that I will show in class. Yeah. So the hope is that, like, once you see everything and how to do it, at least for edge, can you get motivation to make it work for vertex case? So, so this is really nice problem. Yeah. Yes, very important. This is for undirected graph only. All of these are for undirected graph. And the reason is that if you can solve MaxFlow, yeah, we don't know how to do it in directed graph, yeah. And this is actually open even for like unweighted graph too. Even for unweighted graph. But this one works for weighted graph as well. And this also works for weighted graph. But everything is for undirected. Okay. So last thing, maybe that I will tell you today, is that next week we are gonna see actually that if you have undirected graph and you have S and T, and you just want to know if S is connected to T, if there is a path from S to T. So the graph might not be connected, right? The graph might be like this. T might be here.